Hello everyone, I'm Musa, a PhD student at Level University. I want to talk about our new proposed multiple level downshifter, which is a reconfigurable single supply structure for system and chip applications. Welcome to my presentation. I organize my speech as you can see here. Introduction, proposed reconfigurable single supply level downshifter, circuit implementation, results, performance comparison, and conclusion. Dense integrated systems regrouping many building blocks like system on chip and system in package require different voltage supply levels. Thus, level shifters are essential circuit in both SOC and SIP to allow signal compatibility between all building blocks. Designing a high-performance level downshifter with low power consumption and short propagation delay is challenging. It is worth noting that conventional level downshifter circuits need a whole lower supply voltage when downshifting a higher voltage signal to multiple lower signals. Such a configuration is illustrated in part C of this figure. While the proposed single supply level downshifter needs only one supply. Besides, it is a reconfigurable building block. The proposed level downshifter circuit is based on the particular operation of a diode, the anode of which is connected to the supply and the cathode of which is synced by a current source. As shown in part A of this figure, the amount of dropped voltage across the diode VAD depends on the amount of synced current from its cathode IAD. Part B of this figure illustrates the reconfigurable scheme and how a single supply is used to multiple voltages, VD1, VD2, and so on, and V prime to the output buffers. Part C of this figure shows how the diode connected architecture is controlled dynamically by the input signal with the highest voltage. This figure shows the transistor level implementation of the proposed circuits. It is composed of different sub-blocks. In this circuit, when the input signal level is high, the requirement of a source gate lower than the threshold of MP11 must be met to avoid MP11 from being turned on. In addition, in all settings, the circuit must be able to deliver enough driving current from VDD to V prime to drive a considerable capacitive load with the output buffer. When the input signal is low, MP6 is turned on to put MP1 in a diode connected transistor configuration. The proposed circuit was implemented in a standard 0.35 micrometer AMS CMOS technology. This table presents the post-layout simulation result of the presented circuit at a 3.3 volt supply voltage and an operating frequency of 1 MHz for three output levels of 1.2, 1.8, and 2.5 volt. The important parameters of this design are the static power consumption and the dynamic power consumption, the rising and falling edge propagation delays. This figure shows the post-layout simulation of the presented circuit when it is configured to provide a pulse level of 2.5 volts. The top part of figure shows the result for a 10 picofarad capacitive load, and the bottom part presents the performance of the circuit with a 350 picofarad capacitive load. The performance comparison of the circuit with this recently published works is presented in the table. The privilege of the proposed methodology is being single supply, reconfigurable, and capable of driving large capacitive loads. Finally, I would like to thank you for your attention. If you have any question, I am pleased to answer.